Water vapor and vapor pressure deficit. This presentation was developed by Dr. Thierry Kubota and Dr. Mura Kachira from the University of Arizona. The content of this presentation includes plant responses to water vapor and key water vapor parameters in controlled environment such as relative humidity, vapor pressure deficit, VPD, and leaf-to-air vapor pressure difference. So the following two slides summarize the plant response to water vapor. First of all, transpiration, as you know, generally increases as humidity in the air decreases. However, transpiration rate is determined by many factors, including humidity, temperature, light, air current, water availability in the tissue. So humidity of water vapor is not the only factor affecting transpiration rate. And then also you will learn that humidity can be expressed by many different parameters. Therefore, understanding properties of moist air and the influence on water loss from the plants and harvested produce will help to selecting best CEA practices. Also, we know that stomatal closure is indirectly or directly affected by low humidity. And when stomatal opening is affected by humidity, then CO2 exchange rate, which is net photosynthetic rate, is affected also by stomatal opening because the gas exchange of CO2 and water vapor shares the same entrance, which is stomata. And transpiration acts as very important cooling mechanism in plant energy balance. Therefore, humidity affects plant temperature through the transpiration. So let's define relative humidity. Relative humidity is the most simple and widely used parameter, and it is computed as percent water vapor pressure over the saturation water vapor pressure at the same temperature, as you can see in this equation. By the way, water vapor pressure means water vapor concentration in a volume base. The use of partial pressure is a common practice in physics to express the concentration of gas. So basically, relative humidity means the ratio of the current concentration of water vapor and the potential saturation maximum water vapor concentration that air can hold at that temperature. Okay, saturation water vapor pressure actually increases with increasing air temperature, and then that increase is almost exponential. And this is an empirical equation showing that rapid increase of saturation water vapor pressure with increasing temperature. And the increase nearly double for every 11 degrees C or so. So as you can see, 10 degrees C, the saturation water vapor pressure is a little bit above 1000 Pascal or 1 kilopascal. But when it is 20 degrees C, it is above 2 kilopascal or 2000 kilopascal. So it's about every 10 to 11 degrees C, the amount of water vapor that air can hold, maximum amount doubles, as you see in this diagram. So it is basically telling that the capacity for the air to hold water vapor increases rapidly with increasing temperature. So going back to the relative humidity, which is the percentage of the current water vapor concentration to the saturation, and because the saturation status changes according to the temperature, same relative humidity doesn't mean the same capacity to hold that moisture when temperature is different. For example, 60% of relative humidity at 40 degrees C has much more capacity to hold the water vapor than, let's say, 60% at 10 degrees C relative humidity. Amount of moisture or water vapor that air can hold at the same relative humidity is very different at different temperatures. So to include that understanding, temperature affects the holding capacity or water holding capacity of the air, we use the value called vapor pressure deficit. The vapor pressure deficit is recommended parameter to measure moisture in the air because it is directly related with the capacity of the air to absorb more moisture. So the directly determining evaporation, potential evaporation rate in that air. So VPD is the difference between the saturation water vapor pressure and current water vapor pressure at the same temperature. So it's a concentration difference between the current and also saturation. So it's simply expressed with this equation: saturation vapor pressure minus the current vapor pressure. And then unit is, because it's a pressure, kilopascal is the unit. Remember, the relative humidity was the ratio of the two, but vapor pressure deficit is actually the difference between the two. And VPD indicates how much more moisture or water vapor the air can hold. So if you show the relationship between VPD and evaporation rate, then the relationship should be linear like this. More the VPD or greater the VPD, then more water holding capacity for the air, therefore more evaporation rate can potentially occur from the surface of the water. This table is showing vapor pressure deficit of different temperatures and different humidities. So 10 degrees C, 100% relative humidity. This is a saturation situation. And then this is a saturated water vapor pressure. And because the saturated water vapor pressure, VPD is 0. 60% relative humidity at 10 degrees C, meaning the current vapor pressure is 60% of the saturation. Therefore, 60% of 1.28 kilopascal saturation is 0.74, and vapor pressure deficit is the difference between those two, therefore 0.54, and humidity 20% is 20% of the saturation, therefore 0.25. The VPD is the difference between saturation and current, so 1.28 minus 0.25 is 1.03. So note that humidity decrease, then VPD increase, because VPD is the capacity for holding more moisture at that temperature. So the same situation, 20 degrees C, 100% humidity, saturation is 2.34, 60% humidity, meaning 60% of the vapor pressure contained in the air, so 1.40. So VPD is the difference, 2.34 minus 1.40 equals 0.94. So that's the table it's showing to you, the relationship showing VPD, temperature, and humidity. To find those values, there are multiple resources available, and this is a classic resource we call psychrometric chart. This is a piece of paper, and you can find out the VPD, vapor pressure, based on temperature and relative humidity. And this is a relationship between vapor pressure deficit, relative humidity, and temperature. So this big table, columns are showing relative humidity, so 0% to 99% relative humidity, and rows are showing temperature, Celsius. And then the values in here showing the VPD computed at that combination of each combination of humidity, relative humidity, and temperature. And pink value is showing the VPD range between zero point 0.3 to 1.3 kilopascal, which is actually a good BPD to grow plants, and showing that wide range of BPD at relatively low temperature, but very narrow range of BPD at higher temperature, because saturation vapor pressure increase rapidly, exponentially with increasing air temperature. Okay, so there are a couple of confusions I would like to point out here when we talk about BPD. First of all, BPD is a vapor pressure deficit and the pressure unit we use. However, some growers prefer to use mass per volume concentration unit for vapor pressure rather than partial pressure unit. So saturation vapor pressure now in grams per cubic meter, and then the current vapor concentration is also grams of moisture in the air of cubic meter. And then in that case, you can also compute the difference between saturation and current, but the unit is grams per cubic meter. And then in this case, we specifically call that humidity deficit. However, the conversion coefficient is temperature dependent. So this one is the equation to convert VPD to humidity deficit. And this table is showing the conversion factor from VPD to humidity deficit and from humidity to VPD. For example, at 10 degrees C, if 1 kilopascal of VPD is recorded or found, then humidity deficit is 7.65 grams per cubic meter. So that's the relationship. Another terminology confusion I would like to point out here is BPD utilizing leaf temperature. So concept behind that, the BPD as we define, it's a difference between saturation air vapor pressure and the current vapor pressure. However, some people use BPD, including the concept of transpiration from the cell. So the stomatal cavity is usually saturated with the moisture, and then the saturation is determined by the leaf temperature. So that level of vapor pressure is EL, saturation at the leaf temperature, and then that moisture comes out through the stomata, and then it's a diffusion driven by the concentration difference between the vapor concentration in the cavity and then also vapor concentration in the air. So transpiration rate is directly related or proportional to the difference between those vapor concentrations. The leaf to air vapor pressure difference is sometimes used. So again, this is the difference between saturated vapor pressure at leaf temperature and vapor pressure of the air, EL minus EA. And then if you specifically look at this particular leaf, EL minus EA is determining the transpiration rate of the leaf. However, the challenge of this concept is that the EL value, so the saturation vapor pressure at leaf temperature, is very difficult to find because leaf temperature is not uniform throughout the plant production system. So which temperature should be used to compute the saturation vapor pressure is always the challenge. Therefore, in controlled environment agriculture, particularly agriculture, horticulture, engineering, this concept is not so well utilized. Instead, VPD in the air, vapor pressure saturation at the air temperature minus the current vapor pressure, is more widely used in the plant production system. So there are a couple of further reading. Thompson, this is a chapter in the textbook in post-harvest technology in horticultural crop. This is good chapter for understanding psychrometrics if you are not familiar with psychrometrics, because we don't cover psychrometrics in this presentation. And another thing is the online accessible resource, growth chamber handbook, and that is also good resource to understand humidity and psychrometric chart. Thank you very much.